Now, I will start with that why antenna radiate. Now, very first thing that what is antenna? In a layman language, we can say that one is the transmitter, another is the receiver. So transmitter and receiver, the one is transmitting. 1 minute. Here we can say a system where electromagnetic wave transmitted and received. So whatever the electromagnetic waves are there, they are transmitted from one antenna and received in another antenna. This is what we are going to discuss. Now there will be the transmitter system and all these things that already you have studied in principle of communication, and the receiver system is also there. So in this subject we are not focusing that, we are focusing only the transmitting antenna and receiving antenna. So how the transmitting and receiving antenna, there is how transmitting antenna transmit, how receiving antenna receive, and what are the antenna's properties, and how it happened. So very first, the basic question sometimes that we have to understand that why antenna radiate. So for understanding this answer of this question, you have to go for the previous. What previous? In your electromagnetic. Now, in your electromagnetic here, very first that before going to that, directly I'll go for the radiation. What are the requirement of radiation? Okay, so radiation is a phenomena related to the time varying current. Now here there is two current. One is the time varying current and another is the alternate current. Sorry, DC current. Now, what is your time varying current? Now, suppose this is what your this reference axis. Okay, this may be the voltage or current, and if this is your reference, so this is a time. So here you can consider time. So in your DC current, this is what a straight line. Okay, so in a DC current, what this is what your straight line with a particular voltage or current. But in a alternating current, now if we will see, if we will take the alternating current, so what will happen in the alternating current? Your positive half cycle, negative half cycle, and so on. So here this is your positive half cycle. Here this is negative half cycle. Okay. So here it is what? Suppose I will take this as the current I. So it is positive and negative half cycle. Here what has happened? No positive. Here it is a steady, continuous. So continuously steady is there. So this is what your DC current. This is what your AC current. Now here time varying current. So this time varying current I have given here the sinusoidal. It may be triangular, it may be square wave. Any form of wave comes under this. That is what? Time varying current. Okay. So what is the basic requirement for radiation? For radiation, you require a time varying current. Okay. So now what will happen with this time varying current? So for this time varying current, what will happen for this time varying current? Now we will go for further understanding. Now in this time varying current, for non-time varying current, there is no acceleration or change of the continuously. So there is no acceleration of the charges, and what consequently no radiation. So you will have radiation only and only for the alternating, that is time varying current. If you will have a time varying current AC, that may be sinusoidal, that may be the square, triangular, any form, then and then radiation is there. So other why it is not happening for DC? Because DC there is a constant current, as the graph we have seen. The constant current is there, so there is no acceleration or deceleration. What is acceleration? Rate of change of velocity. Velocity of what? Rate of change of velocity of uh, electron. That is the current. Okay. So rate of change of acceleration is not there. That is the rate of change of the electron velocity. Now, here, no matter how slow the current varies, there is always possibility of radiation. Although, if you will have a larger variation, means for the higher frequency, obviously the radiation is more. For lower, it is comparatively less. Okay, up to certain frequency. So, if it is the time varying, then always there is a possibility of radiation. Then, a whatever you are conducting wire is there, it is radiates because of time varying current or acceleration or deceleration of charges. So here, what is the main concept? That is acceleration and deceleration of the charges. Okay, acceleration and deceleration of the charges. So how it happened? So if you will have this any alternating signal, so you can have any sinusoidal signal or any other signal. Now here, if I will see, this is the current. This is the current I. Okay. So for this current, there is acceleration. But here, this is current and this is your time. So here it is the I is here the number of electrons. So here it is 0. The number of electrons are increasing. Here the maximum. Then again decreasing. Now it is flowing in this direction, suppose. Now again 0, and then they are changing the direction in opposite direction. So if you will take a partial differentiation, so rate of change of this current with respect to time, it is there. This is what the basic concept. So this rate of change is there. So that's why this acceleration and deceleration takes place. So due to that, the radiation is there. Now we'll go further. If there is no motion, no motion of charges in the wire, no radiation takes place. So what again and again I'm saying that if there is DC current, there is no radiation. This is what the basic concept. So radiation will not occur even if the charges are moving in uniform velocity along a straight wire. However, charges moving with uniform velocity along a curved or bended wire will produce some radiation. So this is what straight wire it may not produce, but bent wire it may produce. But this is what very insignificant. So very basic requirement is you must have the time varying current, that is create the acceleration and deceleration. Okay, so if the charges is oscillating with a time, so radiation occur when every along a straight line. Now we will just see why antenna radiate. Here the electric field, and this is what the antenna structure. So how radiation is there? So this is what electric field it is in the antenna, maybe horn antenna or any antenna you can say. And sorry. So here the antenna, whatever the electric field, these are the arrows are shown here so that we can understand and reflect here. So these arrows are taken in the antenna. So but the difference here is here it is a source and this is the transmitting line. Okay, this is transmitting line and this is what your antenna, and it is radiate. So this way the electric field now here the electric field is converted into the radiation. So that way it is producing in the space. So this is what the wave that is in a free space wave, this way it is get radiated. So this is a very basic concept. Now if you will have this curve, if the core is there, so if you will have this curve or if you will have this bend, so then due to this curve or the bend, then there is a radiation. Whether so this curve and bend, this curve or bend, it will produce a radiation. As this is the curve, you can see the radiation. So in designing the antenna, this is what the aspect. If you will see the antenna, it will have the curve. It will have some bends. Or if you will have a disconnectivity, as you are saying that the diameter of both the wires are dissimilar. So again here the radiation is there. If you will have this straight wire, again I'm talking this for all the time varying current, again the radiation is there, and straight wire, again there is the radiation. But if you will have a core and bend, so radiation will get improved. So what, for the understanding purpose, I'm just showing you a bend wire, that is 90-degree bend, and it is a simulation. So you can see that how this bend wire will get radiated. So this is what the black one is, the wire, it is treating as the antenna, and this is what the intensity, as the red dark red is the high intensity and blue is the low intensity. So you can see the here at the bend, as there is a bend, how it will get radiated, it will spread this way, and here at the end also it just goes and then come back. So at the bend, the point here is at the bend there is more spread as compared to the line. So you just see clearly, this is what will give now at the bend. Now it is radiating, although in along the straight line there is radiation. So the intensity, you can see the intensity. So here the intensity is shown. So at the bend there is a radiation. Here you can see. Okay. So this way the radiation takes place. This is what the concept. So this single animation, maybe in the 1 minute, we can understand that what exactly the radiation takes place. Now, in this
Sir, you are on mute.
is the screen visible?
Yes, sir.
Okay. So this is what the how antenna radiate. This is what we have discussed just now. Now there are some type of antenna, that is dipole antenna and all this. So we will, I am just giving you the glimpse so that you can understand that how radiation is there and how there is a change in the radiation pattern. So this is lambda by 2 dipole antenna. So this is lambda is the wavelength. Now what is wavelength? Here, whatever the length of antenna, you can see here, whatever the length of antenna is equal to the half cycle. Now what is this half cycle? This half cycle is not a time varying this half cycle. What is this half cycle? So I'll just it is lambda by 2 dipole antenna. Again the lambda by 2 dipole antenna. Now what is this lambda by? First you get the concept of dipole or lambda. What is lambda? Now here anybody can give me the formula for wavelength. What is wavelength? Relation between frequency and wavelength. F is the frequency equals to
1 by lambda.
sorry 1 by
Lambda.
1 by lambda. No, frequency equals to 1 by time period. So it is not 1 by lambda, it is something is there.
V by lambda.
C by lambda. Okay. So it is C by lambda. So it is C by lambda, correct. What is C? F is the frequency. What is C? Anybody? Quickly.
Speed of light.
Velocity of light.
Yes, speed of light, velocity of light, correct. C is speed of light. How much it is in free space?
3 into 10 raised to 8 meter per second.
Yes, correct. So it is 3 into 10 to the power 8 meter per second in the free space. Same is the velocity of electromagnetic wave in the free space. So we are taking same. Now, here, what is this concept? This formula you are aware, F equals to C by lambda. Now, this F equals to C by lambda is the formula. Now, here, this formula we are getting here for the understanding purpose. What we are understanding? We are understanding here that how this wavelength is depend on this. Wavelength is depend and how the radiation is there. What is lambda exactly? You can say the physical significance of lambda. Now, if you will go for, I'll just go further. So this is what your lambda, and here this is 3 lambda by 2 dipole antenna. Now 3 lambda by 2 dipole antenna, what it is? Now I'll just, this 1, 2, 3 waveforms are there. So before that, I'll just explain you, that is what is this lambda. For this lambda, I'll just take the example here. What again I'll just draw a waveform. So again here it is the one cycle. Now generally we take here, this is the current axis, and here we are taking, this is a time axis. I am trying to give you the physical significance of lambda. This is the time axis. Now what is happening? This current is flowing along the time. Okay, positive half cycle, negative half cycle, as I shown, forward and reverse direction is changing. But in the lambda reference, what I will do, I will just consider not only the time, but I will consider the distance. So the distance may be in meter, or I can put a D. Okay. So this distance, what is happening here? My electron, as you are showing, that electron is moving forward in this direction. If I will consider one electron, so this electron is moving forward in one direction, and this electron is moving backward in the other direction. So it is going forward and backward. Continuously it is happening. Now what is this lambda? So I'll just calculate the formula for the lambda. So here, if I want to calculate the lambda, I'll just put here L. So that is, consider this as a lambda. So lambda equals to what? C by F, am I right? Lambda equals to C by F. Please give me the confirmation.
Yes.
Yes. Okay. So what is your C? 3 into 10 to the power 8. Okay. 3 into 10 to the power 8. So I'm putting this 10 to the power 8. Okay. This one. And divided by, suppose I'm taking this frequency as 300. Yeah. Yes, 300. So what will be my lambda? Lambda, I'll take this as the capital N. So this is what my lambda. So this is my lambda equals to C by F. So can you just give me the value? That is 3 into 10 to the power 8. It is not 108, huh? 10 to the power 8. So this is C value that you are there. So what will be the lambda is how much? 1 into 10 to the power 6. Okay. So 10 to the power 6. 1 into 10 to the power 6. So how much this is? What is the unit? Unit will be meter. Unit will be meter. So how much this is? L lambda will be. So this is meter. So I can take this is kilometer. So how much kilometer will be there? 10 to the power 3 you can remove. So it becomes 1 into 10 to the power 3. Okay. 1 into 10 to the power 3. So it is how much? 1000. I can write kilometer. Is it okay? Is it correct? If this meter I'll convert into the kilometer, is it correct?
Yes, sir.
Okay. So this conversion 1000 kilometer. So what is happening actually? The here it is going 500 kilometer. 500 kilometer it is going forward and 500 kilometer it is going reverse. This is 1000 kilometer here. At this point it is 1000. Okay. So here it is 1000 kilometer. Here it is 500 kilometer. So if you will take for this is true only for which frequency? Not all frequency. It is true only for this frequency. What is this frequency we have taken? 300 hertz. So for the 300 hertz, it is going forward. How much? 500 kilometer and it is coming reverse 500. So what is lambda for this frequency? Lambda for this frequency is 1000 kilometer. Okay. Now, if I will take a frequency, if the frequency if I will take here f frequency equals to again 300, but not the 300 only hertz. So 300 gigahertz. 300 gigahertz. So quickly, can you give me the lambda? 300 giga means 3 into 10 to the power 300 into 10 to the power 9. So 9 plus 2, 11. So how much I will get? 10 to the power 8 and minus 11. So it is minus 3, 10 to the power minus 3. So 0.001. Is it correct? Is it correct? Anybody can give me the calculation. Simply 300 gigahertz. 300 gigahertz means 3 into 10 to the power 300 into 10 to the power 9. So the lambda by this formula, the L equals to C by F. So is it 0.001 meter? Quickly. Is it okay? Is it very difficult calculation? Okay, so I got response in the chat. Yes, so it is okay. So now we can have this much is equals to 1 mm. Am I right? So it is 1 mm. So what 0.5 mm it is going forward and 0.5 mm it is coming reverse. So this is for the higher frequency, the wavelength is very short and everything in the antenna design is wavelength dependent. We are the meter in general case. Suppose I want this table. So the table unit, if I am to design, so I will take a unit in terms of what? Meter, centimeter. Okay. But in antenna design, we have to take the electrical length. It is called electrical length of antenna. Electrical length of antenna, as we have seen that lambda by 2 is what? Electrical length of the antenna. Electrical length is lambda by 2. Means for whatever the frequency you are using, if you are using for 300 hertz frequency, then it is how much? Lambda by 2. Then the wavelength is 500 kilometer. The size of antenna should be 500 kilometer. If you are using for 300 gigahertz, then it is 0.5 mm. So this much difference is there. So this is what called the wavelength. This is the concept of wavelength. I hope that you understood this. So this is what wavelength dependent. Everything in the antenna, it is wavelength dependent. So this is what the concept here, what we have. I'm trying to give you the concept. Now, the basics of this, that how antenna radiate, that we have discussed just now, that due to the acceleration and deceleration. But can you correlate with the Maxwell's equation? As we are seeing this, okay, as we are saying here, that because as I told that we require a basics, okay, what we require? We require a basics of the electromagnetic. Now, as we are saying that we require basics, so Maxwell's equation is the must. Now, can you just tell me that which Maxwell's equation will give you this radiation concept? What acceleration and deceleration just now we are discussed. Anyone can just give me the Maxwell's equation concept? Why, which Maxwell's equation is required? Any idea? Okay, so I will just give the concept. Now here it is the current. Now very first understand the current. There are three type of current. So very first is the conduction current. Now this conduction current, as you have seen in all basic electrical engineering, that is Ohm's law, obey it, rate of change of the current electron. It flows through the wire, it obeys the Ohm's law. So all your electrical parameter, electrical concepts based on this. This is what your conduction current. You are studying this, you know this. Okay. Then the second is the convection current. Okay. So what is this current? So this convection current, when you are, if you will see the CRO, cathode ray tube, cathode ray oscilloscope, and in that there is the CRT, cathode ray tube. Okay. Now in the CRT, what will have the electron? If you will see the conventional CRO, the electron gun is there, and the electron bombard on the fluorescent screen, and then you can see the whatever the waveform is there. Okay. So the electron continuously bombard on the fluorescent screen. If it is the sinusoidal signal, so that continuously bombard accordingly. So it create a fluorescent screen light, and then you can see, okay, this is the sinusoidal waveform or whatever the waveform is. So that current is the convection current. So this convection current, electron are flowing through the vacuum. So vacuum tube and all these concepts previously was used. As similar, familiar to you is the CRT, cathode ray tube. So this is what convection. But the most important for the antenna radiation is the displacement current. This is what the displacement current that you should know. All of you should know this. And if you understand the displacement current, then and then you can understand the antenna, because the fundamentals are very, very essential. I am continuously repeating that if you are not able to understand the fundamental, because it is the base, and then whatever the parameter based on that you are not able to understand. So that's why I'm saying this. So here the displacement current is there. So this displacement current, how it get displaced, means what this displacement current is there. So we require this. So we'll try to understand this displacement current, that is what is displacement current through the Maxwell's equation. Now, what Maxwell's equation we will use? This is for a static field. Now we'll start from the static field and how Maxwell's go for the equation for time varying field. Now this is one of the Maxwell's equation, del cross H equals to J. Okay, so for the static electromagnetic field, this is what Ampere circuital law. This is simply the Ampere circuital law. Del cross H equals to J means whatever the magnetic field is there and this current H is the magnetic field strength. So the curl of divergence of the curl of H equals to G. This is already there. Now, but the divergence of the curl of any vector field is identically zero. This is mathematics. This is simple, the mathematical rule. That is, divergence of curl of any vector field is identically zero. So if I will take a divergence of this, we'll take a dot product with del operator. So it becomes again on the both sides. So del dot J equals to zero. So it becomes zero for this static field. Now, for this static field, we have one contradiction here. What contradiction? So del dot J. So del dot J, he should not be non-zero. For what? This is what? This is current continuity equation. Del dot J should not be zero. Why? Now we will talk for the time varying field and the DC field. Okay, time varying and the DC. Okay, so for the time varying, whatever this field, it should not be zero. Why it should not be zero? As just now we have discussed that you will have two fields. Okay, time varying and DC. Now what is happening in the DC? This is the straight UF current, and in the time varying, what will happen in the time varying? In the time varying, here the signal is alternate signal. Now rate of change of rho v is what? Volume charge density. Rho v is volume charge. What is the charge in the electric current? That is the electron. Okay, so volume charge density, rho v. If we will take a partial differentiation of rho v with respect to time. So here, if this is the DC current, it is obviously zero because there is no rate of change of what? Number of electrons. The number of electrons are for a constant amplitude. In a DC field, it is remaining constant. But it is not true for the sinusoidal signal or any time varying signal, because here the rate of change is continuously changing. It is increasing, decreasing, again increasing. So acceleration and deceleration is here for the time varying signal. So this cannot be zero. It is not possible for this time varying signal. So what to do? So what Maxwell has done? So Maxwell has assumed that for the time varying condition, there must be some additional parameter. What this additional parameter? So this additional parameter may be something. So he has put this additional parameter. It is called JD, displacement current density. Okay, and now he has calculated this displacement current, and this is JD is displacement current density. So again, putting the same equation, equating with zero, adding the JD. So after adding this JD, this equation, you just equate it. So here, if we will equate this, so my interest is to calculate JD is equals to minus del dot J. Here, this I am equating with zero. Okay, so I put here equating with zero, taken this on this side, so that is minus del dot J. So del dot J equals to minus rho v by dt. Why minus sign is taken for this rho v? Because electrons are negatively charged. So that's why. So again, minus is there, minus into minus, it becomes plus. So rho v, what is rho v? According to Gauss law, you can say rho v equals to del dot d. So you can put here. And this is what the partial differentiation you can take inside. So this is what divergence of the partial divergence of d. So divergence you can remove. So you will get whatever the displacement current density, it is the partial differentiation of d. What is d? You can see you have a relation. What relation? D, whatever your d equals to epsilon E. Okay, so you can put here the epsilon. So this is E is the electric field. So if you will have the rate of change of electric field, as we have taken the sinusoidal waveform. So what is rate of change of electric field? Electric field means voltage is there. Okay, so the rate of change of electric field is there. It is finite for the time varying signal. So this is the displacement current. As the rate of change of electric field is more, then you will have the more displacement, more radiation, and this more radiation will take place. So this is what the displacement current density. So Maxwell's equation get modified, del cross H equals to J plus this displacement current displacement current density. So this will get added here. So this additional parameter, due to this additional parameter, you will have a radiation. So this J is called the conduction current density and JD is the displacement current density. So due to your displacement current density, you will have a radiation. At the lower frequencies, the displacement current density is significantly less. So you can neglect it. But for a higher frequency, it is very prominent. So you will have the radiation. And here, this all the whatever the applications you have between two antenna, that is your TV, radio, mobile phone, anything which is having the transmitting and receiving antenna or use of the antenna. So all these applications are due to the Maxwell. So Maxwell's, he has he don't had the high frequency source in 1873. So what after the Maxwell's, that is after him, this was get proved by the Hertz. Okay, Hertz dipole. Just now I have shown you the dipole. So Hertz has proved the dipole, and this is around after 14 years of the Maxwell's. So here the Maxwell's has changed this equation. So this is what the contribution of Maxwell. Already it has given by amperes, but for the time varying field, this equation is changed. This displacement current density is added. So due to this factor is there. And this is what for the static field. These equations are for static field. There is no displacement current density. So this way we can see that how antenna radiate and why antenna radiate. So these are the basics we have discussed, that how antenna radiate and why antenna radiate. So if you will have any question related to this, then let me know. Otherwise, I'll go for the other topic. Is there any question? Okay, so we will stop here.